Well, maybe I'll, our target start time is approaching. Maybe I'll start with the introduction, which, of course, the introduction is not required. So this is our uh, very dear guest today, Rahul Pandharipande, speaking to us from Zurich about Picard cohomological field theories. Still 2 minutes after, so I'm not sure what to say. We look forward to this exciting talk. And this is, despite this being already entering the second half of December, this is not the last meeting of the seminar. So, okay, right. So now it is 3 minutes after. So with this, I yield the podium to Rahul. So.
Okay, so thanks for this invitation to speak here, and I am going to speak about these Picard CohFTS. And the first thing is this Christmas ornament I drew. That's kind of a picture of them, and I'll try to explain more. So the first thing to say about this talk is that it's pretty speculative. I hope that there's at least some things that I say which are correct. And so that's the introduction disclaimer. And in some sense, this talk is about a conversation I started with Andre in 2018 at MSRI. And the idea is, which has been a while now, almost 3 years. And in some sense, once in a while, Andre and I have exchanged ideas about it, and it's been sitting in my head. And in the meantime, there were some developments, related developments, research developments in my group, and this had to do with studying something a little closer to standard geometry as moduli space of maps instead of this Picard stacks. And then the thing that was somehow important for me, mostly psychologically, was this paper that was put on the archive this year. That's Bay, Holmes, myself, Schmidt, and Schwartz. And that was we prove a version of Pixton's formula on the Picard stack. And this made me somehow feel more comfortable with the Picard stack. So maybe this was slightly psychological. And so then more recently, in fact, very recently, with Dimitri, we've been studying the R actions to make sense of the discussion here. And so to the extent that I say anything correct, it's joint work with Andre and Dimitri. To the extent it's wrong, I have to blame it on someone, maybe Jim or someone like that. And a lot of the things I say here are pretty speculative. So, and some of the things are likely not completely correct. But I think a lot of the things have some kind of correct vein in it. So anyway, so we will start. And so I start here with the CohFTs. So the ideas are, first I'll tell you a little bit about CohFTs, then these Picard CohFTs, and then some applications, and then some things about the Picard stack. So the beginning is 3 types of moduli spaces and 3 types of CohFTs. So in some sense, I have to start here. So there's the familiar one, is the Deligne-Mumford stable curve. So this is what when we study CohFTs, almost everyone is studying these. So the moduli of curves geometry is MGN bar, and I don't have to say much about that here. It's a space. So, but the important thing is they're Deligne-Mumford stable curves. And so this is what I'd call the classical case of CohFTs, and it's a well-defined notion. And since Jim asked for superness, anyway, we're not going to do anything super here. If you want, you can make the whole talk super. But that's, it mostly gives one headache. So we'll just do the even case. There's no signs. And we talk about CohFTs with unit. The unit is when we talk about CohFTs with the perspective of this talk, the unit is kind of a subtle thing, and it'll also give us headaches. But in the world of Deligne-Mumford stable curves, the standard is this CohFT with unit. And the first piece of data for this CohFT is a triple, which is a vector space, which is a finite dimensional Q vector space. The tradition in the subject is that you say Q vector space, but in almost every example, you extend scalars one way or the other, so we're not going to worry about that. You can just view here Q as a field or something like that. But anyway, Q vector space, and then a non-degenerate symmetric 2 form, that's this eta, and a distinguished element of V, which is the unit. So that's the beginning data. And then the main piece of data that the CohFT has is some maps. So you can write it this way. It's this capital omega. It has 2 indices G and N, which tell you which moduli space we're talking about. So we have to do this for every G and N. The data is for every G and N. And then this is just a rule that says that if you give me some elements of the vector space, and I can get you cohomology classes. That's what this thing is. So you can write it as a HOM or anyway. That's the Deligne-Mumford CohFT. And there's some axioms, and they can be said in various ways. And I just try to say these in a simple way, not to be too formal. So the first thing is it should be symmetric with the natural SN action where I can spin the points and I can spin this the vector inputs, and it should be symmetric there. Maybe equivariant is a better word. And the main axioms are the splitting axioms that rule what happens when I look at these boundary maps. So this is the boundary, there's this boundary map, and then there's this boundary map. And the rule there is that, so if it's the second boundary map, the disconnected boundary map, I glue on 2 points, and the rule governs what happens when I pull back the CohFT, the GN one to these pieces, and the axiom says that I can split the pullback in terms of the CohFT on one side and the CohFT on the other side, but then there's this extra point, which is the node, and I split it, so that gives me an extra slot in my CohFT machine, and what I do is I split the diagonal in the standard way there. So that's just an axiom, and there's of course a parallel one for the self node. So I've said 2 things: symmetric, it has this splitting property, then there's a unit axiom. And as I said, this is a little bit of a intricate thing to discuss through this. There's some kind of complicated theme that runs through this unit axiom in this talk. But here it should be familiar. You can forget a point. And then the unit axiom says that when you can forget a point, you can pull back the CohFT on the space with fewer points. And that's the same thing as the value of the CohFT on the space with more points, where you put a 1 there. That's the unit axiom. And the thing that's a little tricky about this is this involves contraction. And when the Deligne-Mumford stable curves, one plays with contraction all the time, but when we go to Artin stacks and things like this, contraction becomes more problematic. Okay, and then there's the metric axiom, which says that for the genus 0, 3 points, this moduli space is just a point, and we can give ourselves 3 vectors. If one of them is the unit, we get this metric point, meaning that's a scalar on the point. Okay, so that's the warm up. That's to remind you, roughly speaking, what a CohFT is. There's examples, they'll come later, but it's this data that starts with this vector space, and it allows you to get cohomology class in the moduli space. And if you follow this, you actually find there's using the genus 0 data, that there's a quantum product, etc., using the genus 0 part of it, and then there's a higher genus part. And okay, so I hope some people have heard some aspects of this stuff before, but anyway, that's the quick introduction to CohFTs of the Deligne-Mumford case. So the first thing we can go is the Artin stacks. So on our way to Picard stacks, in between, there's the way station, which is Artin stacks. And this theory for Artin stacks, as far as I can tell, is more or less in Telemon's paper or suggestions. It's not in this language, and he has a different kind of picture of it in his head, but I think it's more or less isomorphic to some stuff that he says in his paper. So for this, we want to have, so the idea about the Artin stacks is we don't want now to have Deligne-Mumford stable curves. We're happy with the Deligne-Mumford stable curves, but it's not enough for us. We want to consider the Artin stack of all genus G n-pointed curves. So these are pointed connected nodal curves with no stability imposed. No stability imposed. So this means that you can have some kind of chains of unstable rational curves doing whatever they want. And also it means that there's some new moduli spaces you can consider. Like, for example, we don't normally consider these kind of moduli spaces in the case of Deligne-Mumford stable, because they're empty. But these things now occur. And so we'd like to consider to start with a definition of the CohFTs for these Artin stacks, and for these Artin stacks MGN. So the first thing is this the problem. So we want a notion of this Artin CohFT. So I want to say what that is. So first, there's some choices. I mean, there were already choices in the Lean-Mumford case. So the choices here, for example, we put cohomology. That's somehow the standard choice. That could also be, you can think about Chow, you can think about some other things. So the first thing you have to do is pick some kind of cohomology theory for your Artin stack. And I have here my perspective, and so far it hasn't failed, but it might be an issue, is to take the most naive one. So there's three ones I can just say. So one is the Chow theory of Andrew Kresch's PhD thesis. And so that's relatively sophisticated theory, too sophisticated for me in this lecture. If you're interested in the Chow perspective, which is actually a perspective I'll take for at least part of the lecture, a simpler, somehow a poor man's version of this is this operational Chow theory of the Artin stack. And what this is I'll say a little bit about that in a second. And then there's also the cohomology of the Artin stack. And I view these, so let's say how I think about this operational Chow. So what is this operational Chow theory of the Artin stack?
So that stack is no longer finite type, right? Is this,
yeah,
are
yeah,
these
it
things
has some
even
problems,
finite?
yeah.
Is it even finite dimensional? These cohomology theories?
I mean, so the stack is finite dimensional. The cohomology theories, I mean, even so it's the Chow stuff is usually not finite dimensional. Maybe your question is whether the cohomology of this Artin stack finite dimensional in every grading. I suspect that's,
Yes,
yeah, I
that's
suspect
the
that's
question.
true. Yeah, I think that's true. But I mean, first of all, I haven't defined it for you. So the point is that it is true that it's a big thing, but up to, if you're interested in some finite depth of it, it's pretty reasonable space. And the cohomology is only, if you're interested in, like, say, some particular cohomology group, it's only somehow a finite amount. You're not seeing you're only seeing part of it at a time. So maybe I tell you to start with how to think about this operational Chow, and it's also the way I think about cohomology. I mean, I take a kind of naive view of all of this. And as I said, that's somehow, I mean, there is a sophisticated view. There's this construction of Kresch, and then there's a question about comparing this sophisticated view to the naive view, and those are all questions which, as far as I can tell, are not completely settled. But anyway, so what is this operational Chow? So what is the class, this operational Chow? And that by definition, such a class acts on the Chow theory of every family. So that means that if I make a family, so this is an object in that category, some base scheme, and here I mean some finite type, some really, really simple things. So we take some scheme of finite type and some flat family of curves over it with marked points. That's an object for this Artin stack. And one views that as a map from the base to the Artin stack. So this operational Chow class, whenever one comes up with such a family, then this operational Chow class has to act on the Chow groups of that S. Because the idea is you pull it back. And then there's a large number of compatibilities, meaning that if you have two families and this and that, you just define it to be a class that acts every time, and then whenever you have pullbacks, it's compatible. And maybe some other things too. But this is explained, this perspective is explained in this paper. But this is the way to think about it. So you view this, how are we going to think about, and you can think about the same way of cohomology too, is that how you think about it is just that it's a class, you can test it, it lives on every family, and it somehow lives compatibly on every family. And that whole Chow group, the operational Chow group, is every such assignment. So this is a very kind of naive view of that. And the problem with this naive view, so the good thing about this naive view is that it's easy to think about. The bad thing about this naive view is if you want to start proving formal properties, then it's not so pleasant. And that's why Andrew has a more sophisticated view. And there's this issue about comparing them. And I think, as far as I can tell, that's still an open question. But nevertheless, we're going to go with a naive view. Otherwise, I'd have to give you a 2-hour lecture on Andrew's construction of Chow groups of Artin stacks, and I would drown in the middle of it. Actually, last time I looked at that very carefully was when he was a graduate student. So, all right. So, and Artin CohFT with unit. So, what is it? What's the data here? So again, we have this finite dimensional vector space, non-degenerate symmetric form, and a distinguished element. So here's just all the same. This is just the same.
The form now probably takes some coefficients like in point mod JM or something like that. Is that...
No, I don't know. I don't think we need that. I mean, so it's like one can maybe deform that. That's possible. But in the way I'm saying it, I'm not doing that.
Okay.
You could maybe do that. We'll explain in a second. I mean, where that point comes in. So it is true that all of these definitions can be shaken a little bit. So and then I want to be symmetric with respect to the SN action. And the point is that the cohomological field theory here takes values in this operational chow. And then the axioms, the first is the splitting axiom. And you should just say formally these things are just the same as before, the splitting axiom and the unit axiom. Because there are maps and you can just look at the products. So you don't have to write them again, but they're just formally the same. The unit axiom looks like the same, but actually it's a little different in the sense that, so the unit axiom is a little delicate because it appears the same as the DM case, because all the symbols look the same, but it's a little different because there's no contraction. In the Artin stack, when you forget a point, you just take away the point. You don't change the curve at all. So it's a little different there. And then there's the metric axiom, and that's what Andre's asking about. And so we don't do it on the 3 points because you can do it on 2 points because we have the 2 points. And so here I've made it to be this, the metric axiom is that this is the metric is the multiple of the fundamental class. I think Andre was basically suggesting it to be an arbitrary class, more or less, or something like that here. But there's you have to have some axiom that connects the matrix to the 2 points. So this is the simplest one. I think one can perturb that a bit, but let's go with the simplest one. Start with. Okay, and the 3-point one falls from the 2-point axiom. And the basic difference is between Deligne-Mumford and Artin is the issue of stabilization, meaning that here there is stabilization in the unit axiom, and so this is a theory with stabilization, and here's no stabilization. We don't stabilize. So it is kind of reasonable to insist that if you have an Artin CohFT, then underlying it there's a Deligne-Mumford CohFT, because the stable curves are in particular nodal curves. And if you follow these axioms, there's a slight mismatch because of the stability. So if you want your Artin CohFTs to give you Deligne-Mumford CohFTs, you have to do something about the stability. And the simplest way is to just say it by hand, that these Artin CohFTs are stable if when they restrict to MGN bar, you get a Deligne-Mumford CohFT, which has to do the stabilization. And as I said, I advertised at the beginning, this unit thing is a little bit of a headache, and it might be better just to forget about that point.
So just to help us think about, just to help us think about this operational thing, can you tell us what the fundamental class in M02 bar is? Because that M02 bar is some annoying mess of like all kinds of things, right?
Yeah, but
I mean,
here it's not so bad. It's just that it's so if you have how this fundamental class acts is if I take any family of 2-pointed G0 curves, then this acts as the identity on the Chow groups there. That's the fundamental class.
Axis, okay.
And that's going to be compatible for any compatibilities you want, and that's the fundamental class.
What degree does it live in?
0.
It lives in 0. Okay.
Because in the shift here, as I advertised that it lives in the shift is the degree here, and it lives in 0. So the fundamental class is okay.
Even though that dimension is somehow -1,
because that's
lives in 0.
Yeah, it's still okay. So as I said, so maybe we leave this unit business off because it's giving me a headache also. And but if you want, I just wanted to say, if you want an Artin CohFT to give you a Deligne-Mumford CohFT, you need to put something about stability there. So okay, so that's somehow warm up. So first was Deligne-Mumford, which everyone should be familiar with, and there's Artin, which is in some sense very similar, except for these issues, these confusing issues. So then we go to the Picard stacks. So that's supposed to be actually the meat of what I'm trying to say today. And so the first question is, what do I mean by this Picard stack? So it has 2 indices here. the genus and the number of points. And what this Picard stack is, it's a stack that's objects are pointed connected nodal curves. So this is all familiar. And then the new thing, of course, is the line bundle. And there's no stability imposed. There's no stability at all. So you just have a curve. You have a curve that's nodal, and the points, of course, it's a standard thing about the points. The points can't be the same, and they can't be nodal points. And then you put a line bundle on top of it. And there's no issue about number of points on a component or degree, or there's anything. And of course, the line bundle, of course, has its own degree. And that means that this Picard stack is a disjoint union of a countable number of other stacks where I fix the degree, because the degree is an invariant. You can't change the degree. I mean, and it's a deformation invariant, the degree. So often we will write this, we'll just consider the whole thing. I think it tends to be useful to think about this stack all together, all the degrees together. Okay. So we want a notion of a Picard CohFT, and we will use this operational chow. As I said, at some point we'll switch to cohomology when we come to this proposals of classification results. Then we'll switch to cohomology, and you could just in this whole talk you could talk about this operational chow or this cohomology defined in the same way. But there were choices before, and so this is the new direction. And this is, as I said, this is really some ideas that Andre and I were discussing almost 3 years ago, I think now, and it's somehow it's been kind of a long time. So what is a Picard CohFT with unit? So it consists of again this data of this V, this vector space, and this non-degenerate symmetric form, and then a distinguished element. And now I want the CohFT part to give me classes in the operational chow of the Picard stack. And we can separate the degrees. So if I have a Picard CohFT, it's the same as giving actually an operation for every gn in degree, because it just splits. It's just they don't, in some sense they don't talk to each other in this way. Later they will talk to each other, but from the point of view of just designing a cohomology class, they're all separate. So you could put a degree grading here. And then what are the Picard CohFT axioms? Well, the splitting axiom should be approached with a little more care since there's no gluing maps. And this is again a little confusing point. If I have two curves in a node, I can glue them. If I have two curves with line bundles, then I can't really glue them. I'd have to pick some gluing data for the line bundle, and this is a little bit problematic. And I think there are some ways to get around that, but actually for the gluing axiom, if you think about it, you don't need to glue. And the way to do that is that, so I'm trying to explain to you now the splitting axioms. And here what I'm trying to say is you have to be a little careful with the gluing axiom. And so I want to associate to a graph. So if I look at a graph, so let's see, the story starts here. We look at a graph. This graph has two vertices. This is supposed to be the dual graph of the curve. So the vertices are the components, and they should come with a genus label, and they have these markings and a degree. And the second one has, so in the splitting axiom and the normal splitting axiom, we have to figure out what happens to this graph here. That's the usual splitting axiom with just some kind of genus in here like that, or something like that with some, but now we have an extra label, the degree. And anyway, to this graph, we can associate its own Artin stack, which is the Picard stack associated to this graph. And the objects of this Picard stack are families of pointed curves with line bundles with dual graph given by this or a refinement. So that there's actually to this graph there is a actual moduli space. That's the space of line bundles on degenerations. And the point is that they're already glued. That's somehow the point. Because then if I define it this way, then associated to this graph, the line bundles are already glued. So in particular, there exists a nodal section corresponding to the edge. And we have maps from this this Picard stack associated with this graph. it maps to the Picard stack, the full Picard stack. And moreover, so in some sense, this comes already glued. And then for this one, I can forget the two sides. So I get maps the two sides. So it's not a product, but still there's enough structure here to write the splitting axiom. So this is a minor technical point, but I just wanted to be careful about it. So you can write the splitting axiom using the diagram here without the product. Then the splitting axiom means that if I pull back the object here, it's the same thing as pullbacks from these two factors with the diagonal, with the splitting of the diagonal. Okay, so that's a small point. And there's probably other ways to do it, but I'm just trying to say that you don't actually need the product for that. All right, that's one small point. And then you have to do the same thing for the loop, which even slightly more cares native because you need to order the nodes anyway. Then there's the unit
aren't
axiom.
those two cases really quite fundamentally different? Since like if I'm just gluing up line bundles from two separated guys, there's like an extra C star if there's a loop, right? There's
I know, but the way I define this thing is that this Picard, you can define this pick of this graph the same way. That they come in this Picard stack, they already come glued. They come with the data of the gluing, and then you forget that data, which you're allowed to do. I'm not gluing. I'm not taking things that were not glued and gluing them, because if you do that, then you have to pick extra data. And I think you can probably do that too. You probably put that in some other piece of data and do some equivariant construction and quotient out. I don't think this is really a fundamental point. It's just something that one has to be a little bit careful about. But the trick to get around this issue is just for these inclusion maps, you have things already glued.
Are you
okay.
summing on all D1s and D2s that sum up to D in that formula there?
This formula? No, because I already picked this. This gamma already has the split.
Okay, thanks.
Does that answer the question?
Yep.
It's a good thing we're not, because there's an infinite way to write D as a sum of D1 plus D2.
Right. That's
and we're going to come to that infinity too. We're going to come to those kind of infinities. All right, so that the unit axiom is unchanged. It's you just forget the point, but there's no stabilization. And then the metric axiom is we look at the 0, 2, and the 0, it's the fundamental class in this 0. And I think that probably this can also be deformed in some direction. But anyway, this is the simplest. And the stability can be defined before, so we get this idea that if you have this Picard CohFT, you can make it an Artin CohFT by just taking the Artin stack and putting the trivial bundle on it, and then you can restrict that to the Deligne-Mumford CohFT by just insisting it being a stable curve. So they should be somehow. We're getting more and more data here, and if you want to go backwards, the only thing you have to be careful about is the stabilization issue, what I'm not going to mention again. So this is somehow the lay of the land there. All right. So in some sense, I haven't said anything because I've just done some kind of definitions. For this to have any interest, there should be some interesting examples of these Picard CohFTs, and then there should be some reason to assemble the data as a CohFT, and those reason. So I will give the examples in a later paragraph, but the next paragraph is about the reason why this data is a very interesting way of assembling. There's a kind of algebraic structure of this data, which goes by the term of the action of the Giventhal group. And this is what I want to explain now. And somehow the part of this talk, to the extent that I am confident about anything, maybe most confident about this point, because we have been discussing it and also with Dimitri, is that it makes sense to have this Giventhal group action. So the Giventhal group action was used by Giventhal and also by Telemann here in this DM world. And I think more or less Konstantin, when he writes his paper, he's basically claiming it also works in this Artin world. And I want to explain how I think it also should be fine working in this Picard world. And that's kind of an interesting tool, because it's a way of if you have one CohFT, how to make other CohFTs out of it. And the other side of that is classification, which says that classification roughly says that if you're in semi-simple case, you have some complicated CoFT you don't know, it's actually the same as taking some very simple associated CoFT and translating it in this group. And it reduces the entire data, or the entire problem of characterizing your complicated CoFT. It reduces that to the minimal possible issue, which is, I mean, the minimal possible data the problem contains, which is finding the group elements. So that's somehow that's the notion of this given-tall group action, and the classification in some sense is what gives this language some teeth. And so if we don't have it for this Picard CoFT, then maybe it's not really so worth studying them. But I'm trying to propose we do have that there. So let's do the action of the given-tall group.
Sorry, what is topological part of Picard CohFTS?
The topological part is, again, the part that goes to the fundamental class, the component in the fundamental class.
I see.
That you can also say it's the part. I mean, there's, yeah, this is a question that gets to getting ahead of the game. But the question is, what is a topological part of a Picard CoFT? And that's a role. That's an issue that comes up in the classification. And you can just say it's the part that's it's the fundamental. In the CoFT, there's always the part that's the fundamental class. Maybe we'll discuss it when I get to that there. Okay, so for the Deligne-Mumford case, so probably everyone has seen some aspects of CoFT in some language before. I think that the number of people that are familiar with the action given-tall group is smaller, so I'll say say a few words about that. So this is again in the standard case, the Deligne-Mumford case, and there's various references for this. The way I learned about it was reading sections of a paper that Dimitri wrote. I mean, our paper that Dimitri wrote, these sections, they're the best place for me to read to learn this. Okay, so I recommend reading those. And then the paper with Aaron Pixton, these actions are written very, very carefully there. So, Dimitri and Aaron Pixton. So for a Deligne-Mumford CoFT, so there's the standard case. So there's going to be two things. There's the R matrix and the T matrix. And the R matrix is the first one, and it's usually written this way. So I mean, it's a power series in Z, whose coefficients are endomorphisms of our vector space V. And moreover, it should start with identity endomorphism. And on top of that, it should satisfy what's the symplectic condition, which says that if I take this power series and I take the power series that is given by taking the adjoint of all the operators, the adjoint with respect to the metric, then when I multiply this together, I get 1. Okay, so that's the input. And these this is just algebraic data. It depends only on this. And you can check that that actually the set of all of the solutions of this, I mean, the set of R matrices that satisfies all this forms a group, and particularly there's the identity, etc. All right. And so this is called the Giventhal group, and it's a theorem that's, I mean, it's implicit in many places, but let's say it goes back to Giventhal, that if you have a Deligne-Mumford CoFT with this data, and I have an element of this Giventhal group, then there's a new CoFT on the same data, and it's defined by by two basic actions. There's a T action and there's the R action. So I have to tell you what T is. So T is a vector. So this T is a vector. It's a power series in Z whose coefficients are vectors in V. So I will get to this. I'll say this more carefully in the context of the Picard CoFT, but this is what this is the very first statement about the group action. It says that if you, I have to tell you what the group action is, etc., but I'll get to that in a second. But just the way the ideas sit together is if I take this CoFT, my input CoFT, and I take this Giventhal group element, then there's a particular action which involves first translation by this vector. There's a translation action, then there's a Giventhal group action. And then when I do these together, I get a new CoFT, which is R lower dot omega, and that's a new CoFT with unit. All right, and so it's a little machine. They're completely explicit, these two actions. They're just so I'm going to treat them with some care, but right now that's the statement. So is there some formal questions about the statement? So in some sense, what I haven't defined is how T acts on this, how R acts on that. And once I define that, both of these, then I've defined what that dot means. And this is what T is. This translation vector, you take the identity, and I just multiply it by Z. That's and this is a power series in Z with coefficients that are vectors. And so this is one of them. That's a very simple one because it only sits in one place. It only has Z. But this is more complicated. I take the identity vector and I multiply it with the inverse of that R matrix, and that gives me some vectors at every Z stage, and I multiply it by Z. But actually, when I do this, you see there's no constant term because they both have Z. In fact, there's no Z term because it's dies here. So this thing starts out with Z squared, and that's kind of an important feature of it. Okay, so we're going to get back to that. But so on our movement, we go to Artenstacks, and the claim, which, as I said, I think that this claim is essentially in Telemon, maybe precisely in Telemon, is that the R action holds with very few changes. So if we have an Artin CoFT on this data, then there's this, and I have an element of the Giventhal group, then there's a new Artin CoFT given by the same algebraic structure. And as I said, I'm not going to discuss this now. I'm going to discuss the whole thing in the Picard case because there's a few changes there. So now we go to the Picard case, and we'd like this thing. So the first thing is, so there's a richer R actions. So the first thing is what do you want to be in the R? Where do you want R to be? And so the idea is that we put so it's still a power series in Z, but the matrices now we've extended their scalars to involve a new series in L. So these coefficients, this R matrix are power series in V, but they have a new coefficient. They have a new series in L, and this L is related to the geometry of the Picard stack. So it's going to be related to the universal line bundle, eventually related to the theta divisor. So this is some kind of new piece of geometry that's going to come in that has to do with the Picard stack. But the rest makes sense. So that's so from the algebraic point, it's kind of minor. All we do is we change the R matrices. Instead of being Q matrices, they're Q power series in L. All right. And now, because the unit is such a headache to always think about, I'm going to take the unit away, which is already a mathematically interesting thing to do. We can think about CoFTs with no unit axiom. So that means that these CoFTs are built on just a vector space and a form. There's no unit axiom, and it's a good thing to think about them. It's a useful. I mean, it's also in the Deligne-Mumford theory you can think about without a unit. So I'm going to think about this first without a unit. And there's an R action on Picard CoFTs without unit. In fact, somehow in this statement, there are these actions here, and these individual actions don't fix the unit. Only if you do all of this together with this carefully chosen T do you get the unit to be preserved in all of this. So actually, it's more natural from the foundational sense to think about CoFTs without a unit, and think about the actions there first. So I'm going to think about that. So I have an R action, Picard CoFTs with no unit. So let omega be a Picard CoFT here with no unit, and I want this R be an element of this richer Giventhal group that has this L class in it. Then I claim there's a new CoFT that's R acting on omega on the same data V and eta. And how to define the action? What is L? So these are the questions I want to address. And how to define the action is it's kind of the same. But it has, I mean, the interpretations are a little different, and the question about the degrees and things like that now are relevant. So first of all, how do we define the action? So I'm going to try to write a formula for it. It helps, of course, if you know what the action is for the Deligne-Mumford case. And actually, when Dimitri gives these talks, there's this kind of beautiful picture, and I tried to find one on the web, but I couldn't find it. And anyway, so you have to settle with the actual formula. So remember, this is we start with a CoFT omega, and I have to make a new one. So I have to tell you what this new CoFT R omega does on G and N. And in order to figure out what it does, I have to feed it n vectors. So I feed it n vectors, and then it's my responsibility to tell you what the answer is. And how am I going to do that? Well, the only thing I know is this fellow. So I have to do it oh, I know the R matrix and the previous CohFT. So I have to make some machine that that takes the old R, I takes the old omega, and together with the R matrix makes a new one. And the first step in that machine is I sum over all graphs. Because so the answer here has to be some element of the operational child group of the Picard stack. And so I'm going to have to sum over all graphs of this Picard stack, the graphs, so all the strata of this Picard stack. And so what is a stratum of this Picard stack? Well, it's indexed by this graph that was previously a stable graph. Now it's just any damn graph. So it has vertices that correspond to the components. It has edges which correspond to the nodes. There's marking. So I tried to draw locally around a vertex. It has the data, the genus there, the number, the valence, and it has a degree also. Every single graph that's colored this way. I mean, every single graph with this data. So is that set pretty clear? It's just basically you take, for the first you take the dual graph of all possible dual graphs of curves, and then you sprinkle the degree data on them for every vertex. And that gives you all possible graphs for this Picard stack. And then whoever asked the question, is a very relevant question here. There are infinitely many. This is not a finite sum. In the Deligne-Mumford world, this becomes a finite sum because we're summing over all stable graphs, and the finite sum, we're always happy with finite sums. And as algebraic geometers, we don't really do convergence. So if there's infinite sum, you have to think a little bit what this means. So this really is an infinite sum, and it's infinite in several ways. The first is that since there's no stability, forget about the line bundle. With just the actual curve, you can have infinitely many graphs. But then you have a second infinity on top of it, because once you have even a very nice stable graph, you can sprinkle the degree any way you want. So this is an infinite sum, and this summation is some kind of infinite sum. And that's okay. That's the first thing to understand, is that's just okay. And the reason is that this operational child, the way I've cast it, has a built-in convergence in it, because it lives on any test family. And for every test family, the test families are so algebraic varieties of finite type. They only see finitely many strata. They can't see infinitely many strata. So these kind of infinite summations are perfectly fine in operational chow. Okay, so that's the discussion about this sum. Then of course there's the automorphism factor. So we're gonna this R action has a sum over all of this, and then for each one there's some automorphism factor, and then there's a contribution of that stratum. So then I have to of course tell you what the contribution of that stratum is. That's the interesting part. What's the contribution of that stratum? And then the answer for that is that, and this is the same as in the DM case, is that you place the thing you know on every vertex of the graph. This is a little CohFT, you place it, so you have this omega, that's this graph, it has vertices. On every single vertex, you place the little omega, the previous omega. And you don't get confused by that because you don't know how to order the points to the half edges, but the symmetry makes it so it's irrelevant how you do it. So you place that at every single vertex, and then you have to feed it. When you feed it in this graph, so here's the graph gamma, and we sit at a vertex, and it has some half edges that come in. And so on that it has a genus and it has a degree. You place that omega there, but you have to feed it. And when you feed it, there are different types of half edges. One is it could be a leg. There could be some mark point here, like 7. And then if it's a leg, then you feed it this particular vector. I forgot to write the V there. The V, yeah. I forgot to write this. I'm going to VL. So if it's this leg L, then this thing is a matrix with this cotangent line. And what you do is you already to this L, there is an associated vector. That's this VL. That's what you give me at the beginning. And I put here, oh no, what happened to it? I put here, what color? All right, black maybe, VL. So that's a vector. This is a matrix. So the outcome is a vector. And this is where the Z is. And that's the cotangent line. So that's what happens if it's the leg, if that half edge was a leg. You have this little rule here. And the other issue is that the half edge isn't half of an edge. Then if it's half of an edge, that means that it was like, here is the vector, here was the vertex you're looking at. There's some other vertex, and there's this half edge that comes from that edge. So there's no leg there. And for that, that's the rule already in the Deligne-Mumford case. And just use the same rule. You just place this object. This object has a certain meaning. It's some 2 tensor, and you stick it in there, and it feeds both sides. So, I wrote it, I copied exactly the notation in the paper with Aaron and Dimitri. But, this is a specific 2 tensor. You can see what it is roughly. There's some metrics, there's the matrices, and there's a transpose. It's a specific 2 tensor you stick in there. And now I claim you just do the same thing. And what's the difference now? Well, there are these L's that are running around, and of course there's these cotangent lines and L's, and they just run around. They just give you this whole thing is somehow linear in this cotangent line class, and then it also now there's L acting everywhere. So I have to tell you what L does. So the main new point is that there's L's everywhere. So before there were just cotangent lines running around. I didn't explain what they do. I hope that that's clear. When you see a cotangent line, when a cotangent line comes, when you feed a cotangent line into the CohFT, then the CohFT doesn't eat cotangent lines. It only eats vectors. So it just comes out. It just multiplies it when it comes out. So I could write an equation if it's helpful. If you feed a cotangent line times some vector, then this cotangent line just comes all the way out. And that makes sense because this whole thing is some cohomology class that can multiply it by that cotangent line. And there's a similar thing with the L's, but I have to tell you a little bit about the L's. So the main new point is that we have L's everywhere. There's just L's sprinkled everywhere because the L's are in the R. And so what is L? So given a half edge of gamma, L corresponds to the one thing that's new here, which is that there's a universal line bundle over the Picard stack, and a half edge corresponds to some marking. And so that's some P. And I can take the first Chern class of that line bundle, which corresponds to universal line bundle with respect to that point. That's the new person in the Picard stack, and that's what that L is. So in all of these rules, whenever you see an L, you can pull it out. Just the same way as with the cotangent line. And then you could say, well, what about the kappas? There's also the kappas, and that's going to come in the T action. And the kappas, what was before the construction that provided kappas, will now provide something like the theta divisor for the Picard stack. So I don't know whether this discussion here was understandable. It depends a little bit about how familiar you are with the R matrix action on Deligne-Mumford CohFTS, but the summary is that there's some issues of infinity to come to terms with, but they essentially don't cause a problem. Then there's this new geometric object R, which I put in here. I'm sorry, L, which essentially corresponds to the universal line bundle, and the new class corresponding to the universal line bundle. And then everything else just dances as it did before. And now you hope for the best that this really is an R action. And anyway, I kind of think it's an R action. I wouldn't say that wrote down everything completely. With Dimitri, we talked about it a fair amount, and he can speak for himself, but I think he thinks it's an R action. But the matter is a little bit subtle to write down everything carefully. But I think this is an R action. It means it really does.
Is it fair to say that one of the features of going to this sort of Artin world instead of the Deligne-Mumford is that now you can get rid of the unit axiom, get rid of the unit altogether, and still be able to connect the intersection form to the TQFT itself? You wouldn't have been able to do that without the unit in the Deligne-Mumford world, right? Like if you study these TQFTs without a unit axiom in the Deligne-Mumford world, I don't see how you connect the metric to the actual
yeah, you have, because there was a unit there. Yeah, I know,
theory.
maybe it's true, but yeah. I mean, it's true that the metric axiom in the Deligne-Mumford world, yeah, but you can still think about CohFTS without.
But if there's no way to tie them, I don't know. That just seemed like maybe part of the point of going to this art.
Okay, I agree that in the Deligne-Mumford world you have a little harder time with the metric. We could normally use that one. All right, I haven't thought in that line. All right, so but we also need the T action because we're gonna need the unit. Actually, the unit is very strong property. It's important. It's a confusing thing, but if you have a unit geometrically, you don't want to forget about it because it's going to constrain things. So then there's also the T action. I didn't say what that is. So what's the translation action? The translation action now on these Picard CohFTS is you start with some vector. The vector can't have a 1. And the components, so it's a z value, that's the coefficients of the powers of z are this vector. And we ask for there's some kind of convergence issues here that either you have to be starting with z squared. As I pointed out, what came up in the Giventhal theorem only starts with z squared, or if it starts with z, that's something new now in this Picard case, and that's possible, but you need at least one L in there. You need some degree 2. That's a technical point. So then there's a Picard CohFT with no unit axiom, and there's a translation T axiom on that, and this is how it's defined. And this is the same definition before, but of course there's some kind of twists. So this is how to make a new CohFT if you start with an old CohFT and you have this T, this vector. And the rule is that you sum over all additions of points, and we're going to use the old CohFT on more points. And we have to, so if it has more points, then it has some hungry M hungry spaces. We have to feed them, and we feed them always with T. Okay? And then there's some factorials, but then the interesting thing is that, but we want to go back to endpoints, so we push down. So so this equation also has more things that are tricky to think about. Well, of course, there's the standard problem. There's infinite sum, and as before, that's not a problem. Then the other thing is, what is here? In some sense, we're using the contraction map. And I said in this Artin world, because we're going to m points and we're pushing down. This is not forgetting. We're really pushing down. And I said in this Artin world, we don't like the contraction map. So here we make some peace where I wanted to define how to think about this construction in this Artin world, where you take this universal line bundle. So this is our object. We have over the Picard stack, there's universal curve, universal line bundle, and we need to be able to define these additions of points that's happening like in the Deligne-Mumford world. And the way you do that is if you have some particular family of Picard, some particular Picard family, you can start adding some Deligne-Mumford points on the universal curve. That's a well-defined thing. This is a technical point also. I'm sorry about it, but so you add some M stable points and then you forget them with the contraction map. I don't know how to get around this. So this is a little bit of the contraction map coming back. So this is a technical point, but otherwise this translation should be fine. And then so I said I'll put these notes up on my webpage afterwards so you can look at them. If you find things that are wrong or don't make sense, you should tell me.
Oh, can I ask a question on the
Sure.
translation action?
Yeah.
So for instance, there is no eta class.
No, the eta class will come. It'll come because there's this L. This T has L's in it. Didn't I put it here? It has L's. And
but
then
it starts from Z.
What?
But this starts from Z. Like we should put at least one psi class.
I think, yeah, maybe, but if you have it with I think it can happen if there's some other unit there that takes that away. I mean, yeah. That's a good point.
So is there a reason why the R matrix starts from identity? Not
Yeah, so this is why I've discussed this with Dimitri. Is Dimitri here? I actually would like to have an L squared term here.
Yes, I'm here.
Yes. This is a technical question, but it's a good technical question. So I would have liked to put also an L squared term, but Dimitri was against it.
L squared.
Yeah, with no Z. You said that this was a problem, but
Yeah.
I would like to put that in there.
Yeah, no Z and Z squared together are a problem. Yes, it will
No
not be
Z and L squared.
Yeah, no Z with anything. Yeah,
Uh-huh.
it's not a matter of L squared or not. It will not be a commutative action.
I see.
Yeah, but
But
there is
like-
some issue there. But I think you can still get that theta by having some unit where you can apply the string equation someplace. But anyway, that's a really good question that led to some confusion. Anyway, I'm telling you what I know.
But like those classes appear in Pixton's formula.
Yeah, exactly. They do. Exactly. They do appear. The eta classes appear. So it's a good question. I would like to put an L squared there, and I was fighting with Dimitri about it, and somehow at the moment he's telling me we can't do it. But this question will give me some renewed vigor to fight him more.
Okay.
Okay, so so this is related to what Younghan was asking, is that what happens with this T is you start seeing these kind of L to the A, psi to the B, and then you're pushing them down. So you're getting these kappa classes you're getting these kind of enriched kappa classes on the Picard stack that have both the cotangent line and the L. And the technical thing that Younghan was asking is that he would really like to see, me too, this class L squared with no psi in it. And it's being ruled out by those conditions. So everyone's a little unhappy about that. So this push downs to some kind of kappa classes. And this is the one that this one is like the pure theta divisor. So we'd like to see this right there. As it happens, you have to use some kind of string equation to see it. I don't know what the content of all of those comments are. We have to work on it. Okay, so those are the two actions. There's if I have this Picard CohFT, I'm giving you two ways to get a new Picard CohFT. One is you start with any R matrix here. And the second is you start with any translation vector, which is here. You can go in the world and find your favorite one or anyone you want, and then you can start translating your Picard CohFT, and you can then put an R matrix action. And in fact, these ones, they have some commuting property, etc. But it gives you a lot of ways to make new stuff. Okay, so now we come to the somehow the main strength of the theory, which has to do with semi-simplicity and the classification theorem there. And I will get back, I'll make some claims about the unit later, but let's stay in the world now where there's no unit X. So we just have and there's less data there. So this Picard CohFT on a vector space with a inner product, and we say it's semi-simple. So what's the definition of it being semi-simple? And the way you can say this most efficiently is that there's the two tensor that comes from, if I have a fixed two-pointed elliptic curve with a trivial line bundle, then this gives me a tensor V goes to V, meaning my family, specifically, my family is over spec C. The object of this family is an elliptic curve with 2 points and a trivial line bundle. This gives me a map to the Picard CohFT, and I can pull back this class genus 1 with 2 points. It eats two vectors and gives me a map from 0 to 0, and that's a number, so it gives me some tensor V to Q. And semi-simplicity, the definition is that this is non-degenerate. I mean, of course, we have a metric, so we can turn this fellow into a map from V to V, however you want to say it, but there's a non-degeneracy. That's the whole thing for semi-simplicity. That's what the definition of a semi-simple Picard CohFT is. If you give me one of these Picard CohFTs, and I can check whether it's semi-simple by just asking it what's going on for this elliptic curve with 2 marked points. It doesn't matter which elliptic curve, just a fixed one. okay? And so then the claim, this is the first claim that has some teeth. And when I say claim, I mean that at least in discussions with Dimitri, it seemed like not impossible that it's true and there's a chance to prove it. That's the strength of the claim I'm making. All right, the classification of semi-simple Picard CohFTS, and it's better now, of course, if we're doing classification, you should use cohomology, because even for the Deligne-Mumford case, there's no idea how to classify the Chow CohFTS. So use cohomology because at the end of the day, there's some kind of stability that comes in, some stability of cohomology. So the classification says that you start with anyone as long as it's semi-simple. And the step one is you define the topological part. And then once you have the topological part, there exists some R matrix and some translation such that the one you started with is the translation of this much simpler topological one, then followed by this R matrix. All right, so that's the classification statement. So the idea is that you have something has a huge amount of data that's complicated, and then there's a very simple part of it, the topological part, and in almost all cases, that's a much better chance to understand it. And then the whole data, this classification results saying the whole data of this full CohFT is in these group elements, which is rather limited data, or I don't know, whatever. You might think it's a lot of data or a little data, but anyway, it's precisely delineated what that data is. So what is the topological part? So the topological part is itself in its own right a full CohFT, and it's the component of the CohFT you start with that's in the H0 in the fundamental class. Switch now to the cohomology. And I warn you that the fundamental class of this Picard CohFT has a fundamental class in every degree because it's a, and you have to check that this is in fact a Picard CohFT. And let me just say the intuition about this topological part is that CohFTs have to do with classes on the entire moduli space. If you ask what its value on the what its component in the fundamental class is, that's something you can test by taking a fixed curve, because that's if you want to see the fundamental class, then you map a fixed curve in. That's a point, then you measure the fundamental class. So in some sense, this topological part is saying it's just about a particular curve, and that's why it's called topological, because that's the notion of a topological field theory. That means that it just depends on the genus, or just the topological part. There's no moduli there. And we will see that one of the applications of this is about local curve theory, and this topological part will then be about the theory for a fixed curve. And for example, that's a theory of fixed curve. Many of us here have studied that for a long time. Okay, so that's the definition and that's the claim. And the proof, yeah, so to be pursued in the spring. So as I said, this whole talk I think would be normally like in the old days, Andre and I would go walk and walk around the lake or walk to the institute. I don't know, this is maybe too formal a venue for this kind of talk, but anyway, this is the theorem that I proposed that to start the theorem to prove in the spring, and it's the one that in some sense we should have started in 2018 at MSRI. But it says that how are we going to do this? So then, I mean, there's this strategy that Telemon uses in the Deligne-Mumford case, and the idea is you have to boost the genus using the one thing you know that's in that box. And then at a certain point, you have to use this cohomological stability. And so now comes a new thing here, because we need cohomological stability. So Telemon uses cohomological stability for MG, that's the Mumford's conjectures. And fortunately for him, they were proven, not too much before his work, but anyway. And we need now for these Picard CohFTs, we need some cohomological stability for the Jacobians over the moduli spaces of curves. And such results have been proven in precisely the form we want, at least that's my understanding, by these topologists or homotopy theorists, Ebert and Randall Williams. They prove the analog of Mumford's conjectures for the universal Jacobian over MG. And what is that statement like? Well, Okay, we'll get to that statement in a second. So yeah, so I said this slide about proof is pretty hopeful. I mean, you know, take it for what it's worth. Hopefully we can do it. Well, first of all, it has to be true, and then the proof has to work. So it's I said this is a speculative talk. If you're going to go build airplanes based on this, I would hold off at the moment. So adding a unit is an important second layer in the classification because it constrains life. The reason is without a unit, there's two matrices here. There's both R and T. So it'd be better if there was fewer data to fix, and the unit will fix that. It'll fix T. So this is a separate discussion but I'm going to put the claim anyway. And I claim this with slightly less confidence than the previous one, which was already claimed, I would say, not with perfect confidence. But, you know, as I said, all this stuff I think is in the realm of being true. So the claim of the classification of semi-simple Picard CohFTS with unit is that then that T is fixed as before. That's the whole content of the claim. So if it has a unit, it cuts down. If it has a unit, then you only have to look for R because R fixes T. That's because the whole theory has a unit. There's less freedom in the actions. Okay, so that's those are the proposals for what to do in the definitions and classification and semi-simple aspects of Picard CohFTS. Personally, I hope it works out. We will see in the spring. Okay, so now where to go from here? There's many directions. How long have I gone? Like an hour?
Yeah, a bit over an hour.
Okay,
so.
I'm just starting. I hope that's okay.
Yeah, it's fine.
Okay.
Yeah.
So other groups, and in fact, it's funny. This weekend, you just sent me an email about other groups, right, Andre? That
Yes, I did. Yeah.
So once you start thinking about this Picard CohFT, you realize that this is just about C star, because that's what we're talking about a line bundle, a C star bundle, and what's so special about C star? And I think the answer, in some sense, should be nothing. And so I'm going to try to explain what the discussion for an arbitrary group is. So maybe viewed associated to the group C star, but C star is just one, a rather simple group. Well, not exactly simple, but so there's no difficulty. So let's just if we just go with some kind of more modesty and steps that I'm more confident in, there's no difficulty in considering a torus, which is a product of R copies of C star. The geometry there, of course, is the Picard stack. Picard stack is not a stack with one line bundle, but it's a curve with R line bundles. There's no issue there. Everything I said, it changes without any originality. Of course, it might be wrong in all those cases, but the whole discussion I said, there's no difficulty in doing it with R line bundles at the same time. And it was just R tuple of line bundles. And one of the things, of course, is that the R matrix changes now, that there is a variable now for the universal line bundle for each one of the universal line bundles. That's everything else is just the same. Okay. And if we think about how to write this actually, what's going on here? This R matrix, what is this thing? That's some kind of equivariant cohomology of that torus. Those are the generators of equivariant cohomology of the torus. And in fact, it's a certain completion of it and this completion is not fancy. The equivariant cohomology of the torus is already graded, and you just take sums of the infinite sums of them instead of having tried. And so this tells you what you should do for a general group. So this is this instead of calling it the Picard stack, now I call it this bun T. So as far as the proof, I kind of sketched the hope of the proof, and is there anything different in the hope of the proof for the torus case? And there's only one point, which I don't know, it doesn't seem to me it should be too serious, but I haven't read any of this. And you have to promote these Ebert and Randall-Williams stabilities to R tuples of line bundles, some fiber products of Jacobi instead of MG. You need some kind of Mumford type stability for that. I don't know. My feeling is unlikely to be serious, but I haven't, strictly speaking, asked Oscar. So one of the things in the to-do list is ask Oscar whether this is an issue or not. But anyway, that's for a product of product of C star, which is tori, and you can imagine that's not going to be a big deal. So the next most interesting case, of course, is GL. Then we look at actual stack of bundles on curves. Rank R bundles. And then we want to know whether there's a Bun GR CoFT. And then I submit to you again that everything makes sense. Whether it's true or not is, of course, a different issue. Everything makes sense. And here you put the completion of the equivariant cohomology GL, which of course is very simple. It's just the Chern classes. And then everything else, if you think about it, just goes perfectly fine. And then finally,
Question.
yeah.
Suppose you have a group homomorphism. Is it your R actions gonna? So then, of course, if you have a group homomorphism, you have
Yeah, you have a map from this Bun stuff.
Yeah,
right?
then is your R matrix
I think it should be okay because if you have a group homomorphism gives a map the other way on equivariant cohomology. And so I think, yeah, I'm not going to say something perfect, but there's a slide here that's related to that. Let's discuss it at that slide.
Okay.
So specifically, but we still get on GLR. If we want to prove something, then there's a new thing. There's a stability. We need to prove some statement, which I can't imagine that this is the first time this has been encountered, is that if you look at the moduli space of bundles on over MG, you want to look at that universal moduli space, and you need some kind of Mumford stability, and it's obviously what that should be. It should be this kind of colored kappas, where this is the kappa with the cotangent line, and these are the kappas associated with the indices with the other Chern classes. When specifically you need such a result if you want to prove this. So this is for the topologists, and so it's my plan to write some kind of long message to Oscar, but I haven't had the time yet. Okay, and you can view this kind of intrinsically, that if I have Bun GL, then there's a universal curve. And should be, it's not a product, but anyway, there's a universal curve, and there's a universal bundle over the universal curve, and that maps to BGLR, so you can pull back classes. So maybe this is where Andre wants to ask that question. So let G be any reductive algebraic group. I mean, if we're going to be speculating, might as well speculate in the full range of the theory. Then there should be some Bun G stacks and Bun G CoFTs, and the R matrix, and these should be defined in the same way I did before for Pic. And the R matrix then lives in this completion of the equivariant cohomology. And in order to prove it, you need some stability statement, which says that some way to formulate that if I take this Bun G and I let G go to infinity, then the analog of the Mumford statement is that there should be some kappa algebra, which comes from taking indices for the maximal torus, and then there's a natural way to take Violin variance there. And that's, I would think, it's got to be the answer. And if that's true, then probably the whole theory.
That's for the connected reductive group. Right?
Yeah, all right, sorry. Okay. okay. Sorry. If this Mumford type statement is true, then my guess is that all the rest of the theory is in good shape. So then let's try to address what Andre was saying. So if I've been teaching with this tool all semester, but still I must say it confuses me. Here, look at that. So if I have some G1 maps to G2, that's not a good color, sorry. If a G1 maps to G2, then if I have then this Bun G1, so if I have, this is like families of G1 bundles, so then that gives me, this thing maps to Bun GN G2, because if you have a G1 bundle, you get a G2 bundle. And then you get some maps in the other way with the cohomology. So I think, so if you have a CoFT, so if I have a G2 CoFT, then I think I get a G1 CoFT out of it using this map, because the G2 CoFT gives me some operational class here, and I can pull it back to an operational class there. So if I have some G2 CoFT, then that tells me I get a G1 CoFT. And so now the question about the group actions is, you want to say that if I have this R matrix has coefficients in the equivariant cohomology here, this completed equivariant cohomology, and that thing maps to the equivariant cohomology here. So I don't know. I have to think about it, but I think that the R actions are probably compatible. If I do the R action on this side and that side, I think that's what you're asking, but I think that's true. Dimitri
can
can
I
say
ask,
something.
Rahul, can I ask a different question?
Sure.
Like for Picard stacks, there is a, like if we have markings, then there is a big automorphism twisting by line bundles by sections.
Yeah.
Is your CohFT equivariant under that group action?
No, I mean, I'm not imposing that. I mean, you might have your own theory with, I mean, I'm telling you some kind of general framework. If you want to put some additional axioms on it, you can do it. But I'm not making any claim about that.
I see.
Okay, so I think this is a pretty interesting direction for someone to go. I don't think that I'm going to be working, or we're going to be working on the this stable cohomology here. But
this would be like saying mixing this. This previous question was like mixing L and Z, right? I mean, in principle, there are two different variables, but
yes, they are principal. But I mean, in some particular example, they could be related. Yeah, I mean, I agree. Okay, so anyway, I very much hope the answer to this question is yes, about the stable cohomology of Bun-G. And it seems funny that it hasn't been discussed somewhere, because there's a very natural answer and everything. And okay, all right, so that's one aspect. That's for full G. And my feeling is the theory really lives for this full G. And I don't know, it's connected or not. I don't know. But, okay, so examples and applications, and in some sense, all of this was motivated by a single example, at least to what we were talking about with Andre at MSRI in 2018, and that has to do with the local threefold theory of curves. And so I know that several people in this audience have been have thought about this theory, and you know, this theory is like 20 years old now, but it keeps somehow expanding. And one of the ideas for this Picard CohFTS is to control this fellow in the one place where we don't have control. So here's the local theory of curves, and I drew this nice picture here. You have a curve and you have two line bundles, and you see immediately there's two line bundles in this theory. So you want to be, you know, in the previous language, it should be not a pick CohFT, but, you know, like a pick with two line bundles. This is the very first natural example. Of course,
pick two. Pick.
No, I don't know what it just like. You shouldn't call it pick two. I mean, when you write it, it's easy. You write it with two indices for the degrees of two line bundles on top. But if you don't believe that all that stuff I said about groups, you can always make this. You can always look at a little piece of it, which is just the actual CohFT. By taking one of the line bundles being trivial, you can kill that freedom. Then you get really a pick CohFT. But anyway, what is this? Oh, then there's two basic examples, two geometric examples, and there's some kind of twisted theory. So this is the local theory of curves, and then there's a twisted theory where if I have X and I have a torus acting on it, then I can get some kind of twisted theory. I'll make comments about both of them. This one I haven't thought so much about, but it's somehow in the land of closer to Gromov-Witten theory and also quasi-maps. So local theory of curves, what is this? So it's 20-year history. And several people in the audience witnessed all 20 of those years, I think. Nevertheless, we had a curve with two line bundles. And in the first iteration, which was for most of those 20 years, the way we studied this theory is we fixed the curve C. And that's a threefold. That's one threefold. And we want to study the Gromov-Witten theory or the DT theory or ideal sheaf theory of that one threefold. And then there's a lot of methods to how to study this. It involve maybe degenerating the curve and all that, but the whole thing is always about one curve, all right? And the freedom that we're allowing in this CohFT world now is we're going to let these things vary. We want to let the curve vary. We can let the line bundles vary freely, and then you get families. And those are families of threefolds. And then you consider that DT or PT or sheaf theory as a virtual class, and that virtual class pushes forward to give me a class on the base, and that defines a CohFT. That because if you give it any family, that virtual class cuts something on the base. So this defines by I just pick stable pairs here. You can do what you want. But so we fix an integer d, that's the some number, and I want to define, if I want to tell you what this Picard CohFT is, I have to tell you what this data is. And if I pick this number d, then this data v is the equivariant cohomology of the Hilbert scheme of points, maybe localized, and this has a basis. It's a Hilbert scheme of d points. I've picked the d. This has a basis indexed by partitions, and this metric is the Poincare pairing, and the unit is the unit in the cohomology of the Hilbert scheme. So that's what the vector space of this theory is. And then we have to define how this theory acts on cycles, meaning that if I ever find a family, and I can assume it's irreducible, so it has some irreducible base, and I have some family of curves with sections and these two line bundles, then I have to define some action on the cohomology, on the Chow theory in the base. And the way that works is I just construct a family of local threefolds. So this data is really, it looks just like you're having just a family of curves, but actually it's a family of threefolds, because line bundles are the local family of threefolds. And I even drew it in a very Christmassy way here, that this blue thing is a curve, and then there's the threefold given by the two line bundles, like this one's the L1. Sorry, it should be green. L1 and this L2. Okay, but it's more than that. It also has relative to certain fibers. And which fibers is it relative to? Well, that's where the sections are. The points are going somewhere, it's relative to those. So it's actually a relative theory of threefolds. And it could have been, this thing could break in the middle too somewhere, because the curves themselves are allowed to have nodes, and that's perfectly fine. Here's the points, so it's relative to these things, and it's relative to that, and this is already this theory, Gromov-Witten theory or DT. It's okay with these normal crossing divisors. That's the theory there, so that you can have little expansions that come in there. So that's and then you consider that stable pairs theory, and you put boundary conditions along these relative things specified by our vectors. The vectors are these partitions, and they exactly specify the relative conditions everywhere uniformly. And then that gives you a virtual class. And this is if you know about this theory, then you know that you actually sum over the Euler characteristic with the usual Q. So you extend scalars, and I don't really want to talk about it because it's not important for what we're thinking about. And then you cut it, you push down, and that gives you the action. You started with this fundamental class of, you started with this cycle S, and I've cut it for you now, which is the action of the virtual fundamental class. Okay, so there's a million things to check, and I will be the first to admit that not all of them have been checked, but I claim that this gives a Picard CohFT in the axioms that I have defined, and in fact, this is the motivation. This is why Andre and I were talking about this thing in 2018. All right, and this, if you haven't been following the subject for 20 years, and for many of you here, hopefully that's not your fault, because the most basic case to think about is the GINA 0 with 3 marked points, and the line bundles are trivial. This is a really famous basic case that began lots of line of inquiry in lots of different directions, and I made some slide with just, actually I prepared these slides this afternoon, so it was I could have gone further, but there's the quantum cohomology, and then there's local curves and correspondence, and also the quantum cohomology of Nakajima quiver varieties. There's somehow starting also in here, and there's Crepin resolution. It's all on the slide. You can see what's happened, but a lot of these ideas trace back to really understanding very carefully this example, which is really the smallest corner of this CohFT. We're keeping the curve fixed, the points fixed. It's just one little piece there. But now we want to control the whole CohFT, which means we want to know what this machine is. We want to be able to calculate this machine. And really, from the really practical perspective, this means that we want to be able to solve the Gromov-Witten theory in families. And even from the beginning, that was a tool that we used all the time, except the families there were usually equivariant families. I mean, equivariant cohomology is a version of this. But we're doing for every family, not just the families that come from the torus. And somehow that's the whole thing here, is to understand this machine, is to, in this case, to solve the Gromov-Witten theory of local curves in arbitrary families. And the very first step is this step of is this thing, which was solved. So that's good news. And it's semi-simple. That's also good news. So what about letting C vary, but leaving the line bundles trivial? It turns out this is more complicated, but it's somehow more or less on, in some, this, I would say this stuff is really effective in the sense that you can really calculate with this. You can write programs. I mean, this is really in the land of effective mathematics. This is the top one. If we start letting the curve vary and the line bundles fixed, then in many pieces of this were already there, but then with HH, we revisited this after many years using the full power of the R matrix, this R matrix action, and you find there that in order to control this CohFT, this is just the Deligne-Mumford one with the the line bundles not varying, the line bundles are fixed. In order to do that, you have to, the Giventhal theory tells you, Giventhal-Tolman theory, you need to find this R matrix, and then you can use some things that are true here. Like, for example, there's this very simple thing. The divisor equation allows you to look at just some degree 0 parts, and the degree 0 parts are constrained by some growth and decay on rock. So in principle, in principle, you control it. It's kind of a weak statement. It's really very weak. And the question is, can you prove anything with the fact that the R matrix is controlled in principle by everything we know? By the GINA 0 data, by the divisor equation, and by some growth and decay on rock. So the first statement is you do control everything in principle. The second statement is, can you prove anything? And the answer is that control is not so great. And it's very hard to prove anything. And the one thing we did prove, and we proved some rationality statements, but the one thing that you can prove is this kind of Gromov-Witten DT-PT, which actually turns out in this case to be equivalent to the Krepin resolution that Jim likes. They turn out to be just pretty much the same thing. And to prove that, you have to do one non-trivial thing, which is you have to connect the R matrix for one of these theories to the R matrix for the other. And the main non-trivial aspect of that is, in some sense, some analytic continuation. And the matter would be very, very difficult, except that Andre was very interested in this analytic continuation before. And there's a paper in the paper in one of the Moscow journals that has exactly what's needed for this analytic continuation. And it turns out just using that particular analytic continuation of the fundamental solution is done in that paper. If you just pile on top of it, just like piling more suitcases on the camel, it'll carry out the whole R matrix. And this thing, I mean, Andre went a different way with that, to understand those analytic continuations in monodromy and work with Bezler-Kovnikov. Is that out now? I don't know. Is that written somewhere?
No, it sits on my that's a manuscript. It sits on my desk waiting for the semester to end.
So this is like a little piece of that, because it's about one particular analytic continuation, and that was interpreted in the work with Roman in terms of equivalence to the derived category. It's a much fancier thing, but actually that one exact analytic continuation, it's amazing. It's exactly what's needed to carry the R matrix from one place to another. And even some simple things like this is probably, if you want to do this whole theory, in these old theories, you can always do in several different ways. Like you could do for AN. I already put here this AN case, and it's just, in some conceptual sense, it's very similar. You get the AN by taking some orbifold quotient on every fiber. And you could ask whether this stuff is all fine for the AN, and probably it is fine based on this new stuff. But anyway, all of this is still in the past. So what does the Picard CohFTS yield? Although I wanted to say that one of the motivations in the 2018 conversations was to try to have this slide at a much better level, meaning that was it possible to write the R matrix for this theory that we love? There's a unique R matrix there, and to be able to say something effective about it. That was one of the motivations for this pick. We'll get to that in a second. All right, but anyway, what does this pick CohFT yield? It provides some kind of divide and conquer strategy for the general case, because the idea is that you only need this R matrix action, and we know in some sense a fair amount out of it. We don't know what the L's are doing. And one of the ideas is to use the equivariant theory of P1. I'm not sure that's exactly the right idea, but I mean, I think I know how to constrain if this R matrix statement is correct, if the classification statement is correct, I think I know how to constrain. The full theory is the L's vary, but it's not so nice. I mean, Andre had some ideas that there should be some nice way using these kind of shift operators in the L's, and that's something we're going to work on in the spring, okay? We have to find out whether that's true or not. So the only thing I can say here is I'm pretty sure if that classification statement is true, one can control this machine over the entire Picard CohFT, because there's not so much data there. But the statement about what's the best way to express that answer, this is some ideas for the future, which I don't know exactly how that's going to go. But it would be great if there was some nice way. And by the way, that if one controls that L, you can prove. Maybe I make a comment here, because it also motivates me. Actual page, new page after. So this is about ideas from MNOP and Gromov-Witten DT. Those theories, if you study them, say if you have some threefold X, then you can study some ideal sheaves, or you can study stable maps. And if you do this in the right way, here you sum over Q, and here you sum over U, and then you have this minus Q equals e to the IU, then these things are equivalent. And it was found from the very really beginning of the subject, it was understood that if one wants to do this, it's better to do this, have a richer theory. So this is kind of like just regular Gromov-Witten DT. Then there's also some kind of torus equivariant Gromov-Witten DT. This is a pretty important tool that's used basically all the time in the study. And that says that actually if there's a torus thing here, then you can promote all of this. And what I was explaining to Jim actually is that, and that can be viewed as some kind of twisted X family over BT, the classification of torus. But the real statement, the more general statement is actually if I have some family over some base. And so let's just be modest here. This is so a smooth family of threefolds. Then there is still some, say, ideal sheaf theory of the fibers. Actually, it's better now to use the stable pairs theory, because the points get maybe a little confusing about what. But anyway, there's this stable pairs theory of the fibers, and there's also moduli space of maps of the fibers. And the virtual class, when both of these theories, before the virtual class was a number, but in these theories, the virtual class is some algebraic cycle on the base, because you push it down. Before, the push down was a number. And this kind of Gromov-Witten DT in families is saying that the exact same story holds over any base. So it's a much more complicated statement. It's about, and what this is like, one of the outcomes of this control would be to prove like Gromov-Witten DT for these families where the curve and the line bundles are varying everywhere over an arbitrary base. Okay, so those are just some motivations of why we were interested in and what ways to go. But in some sense, one can say the best motivation is to try to really solve this theory.
Question.
Yeah.
So do you then think, suppose we do like whatever local ANs, and then your old argument with Aaron will then boost it up to like complete intersections and projective spaces, or is that automatic, or that requires then?
But we're already happy with complete intersections of projective spaces for the most part.
No, I mean for in families.
Oh, in families. Oh yeah. Sorry. I don't know. I have to think about it. That's a good question. I don't know. Yeah, you could say that we just do the whole last 20 years, we run it over families, starting with this. Yeah, it's possible. I don't know. It seems like a lot of work. I don't know. I have to think about that. But I would say, relatively speaking, we know very little over families. The families we know well are the equivariant. I mean, the over BG equivariant cohomology we know relatively well, but this general statement over families, which is definitely true. I mean, of all the things I said in this talk, this is the one I believe the most. That we know very few cases, and the belief, yeah, I don't know. I mean, Andre, you think this is true too over families, don't you?
Yes.
But it's surprising how few examples there are, and in some sense there's not so many tools. Okay, so I don't know whether I should say something about twisted theories or not.
Rahul, can I ask a question?
Yeah.
Is this semi-simple?
Is which semi-simple?
Um,
Oh, this whole example. Yes, it's semi-simple.
I see.
Yeah, that's the semi-simplicity comes. Yeah, I mean it's semi-simple.
But like family of threefolds.
Oh, family of threefolds. I'm not sure what that means, whether it's semi-simple or not. I thought you meant this theory. This theory.
Yes, yes.
That theory is
That-
semi-simple.
Okay.
Okay, maybe I say a word because,
Semi-simplicity is detected by the topological part, right?
yeah, for
I mean,
example. Yeah.
But
So
if
let
you
me
have can I ask another question? If you have a family of threefolds, do you claim that this virtual comes from a cohomology class, or do you have to deal with this issue?
I didn't make this claim. I'm just telling you that if I have this family of threefolds, I mean,
But
talking
you're
about
saying-
this part of the
Yes.
discussion. Georg, are you talking about this part of the discussion here?
Yes.
Yeah, so the virtual class is a cycle class, and you push forward, and you get an algebraic cycle class on the base.
Yes. But someone said that this omega gn should control this, right? In some complicated way.
Yeah, but so sorry. These are two slightly different things. I mean, it does control it for the case when. So what do I want to say there? So this omega n controls it for. So okay, maybe you're right about that. But the omega n was controlling it only for this local curves.
My localization in someone comes from.
Yeah,
cohomology.
but maybe you're right. Maybe it actually is a cohomology class in the base, in the sense that if I, because I can act on any cycle in the base. Do you agree? I mean, the virtual class will cut any cycle in the base because I think it's okay.
How do you do that? I mean,
because there's a relative virtual class, and you can pull back. So if I have some cycle here, Z, then I can restrict this family over that. And then I can do, I mean, if you look at Baron-Fantecchi, that gives me some relative virtual class here. And if this is pure dimensional, then it gives me some virtual class on this whole thing, which I can push forward to Z.
But you want some cohomology class, right? You want to cut.
Yeah, so I'm giving you some just action on algebraic cycles. It's operational Chow class. It acts on algebraic cycles. If you want a cohomology class, I think that may be okay. If I give you something that acts on chains, then normally that's enough for a cohomology.
But then you have to check why your relative virtual fundamental class is a bivariant class.
Yeah, that's probably true. But I think it's okay in this situation. At least the part that I'm most confident about is the operational Chow. Because I mean, I'm giving you the answer. Then you have to check some properties of that answer. But if you this is not coming from nowhere. I mean, that's like how you prove the degeneration formula. You know, you take you have this relative class and you restrict it to various loci. But I agree. There's some checking that should be done there. These are now getting into rather technical questions.
Yeah. So somehow you use that you have this relative perfect obstruction theory.
Yeah, you have to use the fact that it's a relative perfect obstruction theory. That's what you have to use exactly, because that relative obstruction theory has some pullback properties. I think that question is too technical for this moment. I'm going into my 4th hour of lecturing today, so it's okay. So I'll just say one word about twisted theories and a couple things, and I'll stop. Okay. But this is a good example, and it's a similar idea. It's in some ways similar, in some ways different. But if I claim that if you give me some non-singular projective variety with a C-star action, I can also make some kind of Picard CohFT out of that. And so how do I do that? Is we start with some family of curves with these points and this only one line bundle now. And I have to, again, give you some construction. It's going to be very similar to the one that was before. So out of this family, now I make a family of spaces. And those family of spaces is that out of this line bundle, I can take its C-star quotient with X. Okay? So that gives me, on the level of points, if I have a point in S, I get the curve, and I get some kind of twisted X varying over the curve. Are you happy with that? I mean, this is what happens. Like this is like also kind of quasi-map picture. And then I have these points. And then I want to do Gromov-Witten theory for this XC, this twisted X fibration over C relative to these fibers. And moreover, I want to look in the section class. So the space here is the equivariant cohomology of X localized, the Poincare pairing in the unit. And how do I make my CoFT is I sum, I sum over, I want to look at curves here in some class that looks like it's a section class, but then I have some overall vertical fibers. So that's what I'm doing here. So I sum over all classes in this twisted space that project to the section. And then I put some parameter to measure their size. And then I put the relative conditions in. And then I push forward as before. And the reason why I put the relative conditions in, I mean, it was also true before, is that for the to do the splitting axiom, I break it, and that gives me relative conditions. So I have to have relative conditions when I start with. So this is something I've even checked fewer details about, but I think this thing is very similar to actual Gromov-Witten. So this Picard CoFT, if the line bundle is trivial, I think this is basically just standard Gromov-Witten theory, more or less. I mean, at least in the semi-simple case. But when you have this L twist, then it starts looking something like quasi-maps, but I'm not exactly sure exactly what the, because, I don't know. So take it, or you take it for what it's worth. If you think it doesn't work, then you should tell me, but it kind of looks like it works to me.
But the previous example is just like this example.
Exactly, that's right. It's just like this, except
points.
it's a little different because I don't take, I'm fixing the genus. It's a little different. If you think about it, it's confusing. But here, the genus is the genus of the domain. Look, it's a little confusing, but it's a little bit like it, yes. In fact, I think you can make some. The other one I'm summing, look, I don't know. Yeah. There's something confusing going on here, but it's very similar. But I'm doing something different in these cases. Like here, I'm summing over all of these fiber classes, and I don't do that there. Maybe I could have. And maybe the way to answer your question is that probably you can make something that's a common generalization of both, something like that. Maybe that's the right answer. Anyway. So again, one could hope to try to solve this by this kind of divide and conquer. All right, so then the last thing, we're actually come to the last paragraph here, is the geometry of the Picard stack. So Andre says I can go until 21, 15 more minutes.
Yeah, look, you can go for as long as you have slides prepared. So and you have
I don't have many more slides prepared. As we're gonna make it.
You can go until there's no more audience left.
Is there any audience left? I only see you, man.
Yeah, there's still plenty.
No, there are plenty.
When
there
it
are
goes
plenty
to
of
zero,
people,
then you just stop.
All right, we're still going. So the geometry. So one motivation, as I said, is these conversations with Andre de Masserai, which is to control this theory that we've been studying for 20 years. That's one motivation, and I would really hope there was some really good solution to that theory, which I don't think we have. We have kind of growing. We have a better and better understanding, but it could be better. But there's another motivation, which has to do with what's been happening here in Zurich in the past year or two, is that another motivation is actually to study the geometry of the Picard stack. So this is also happens in Gromov-Witten theory and the CoFTs over MGN bar. By studying those CoFTs, you get two things. One is you can solve Gromov-Witten theories, and the second thing is you get to learn something about MGN bar. It's slightly unexpected bonus, but that comes out. And I mean, one example is this proof of those Pixton relations on MGN bar. Some of the most simple proofs of that use the CoFT. In fact, use specifically this Witten's 3-spin CoFT. So one can imagine that if all of this Picard stack stuff works, we should be able to learn something about the Picard stack from specific CoFTs. And there's some kind of signposts along that way also that we found in the last year. And so again, you have to decide whether you want cohomology or operational chow. But in either case, there's a tautological ring. So this operational chow of this Picard stack, this crazy thing, has a nice tautological ring. And here I recommend, if you want some kind of actual careful discussion of it, You can look in this paper. This paper is 117 pages long. So I recommend starting from the end and reading backwards or something like that. But anyway, but the notion of the the tautological ring is it's not hard to imagine. I already told you what the strata are. So that's going to be one thing. And those strata define operational classes. And then I can throw on top of the points, I can throw in cotangent lines. I can throw in these colored kappa classes that have cotangent lines and the universal line bundle. So there's not any, I mean, there's not any difficulty in defining this tautological ring. And the outcome of that, one of the outcomes of that paper, maybe the main result of that paper, is the proof of Pixton's formula. So you can also define a double ramification cycle in that Picard stack. And somehow the main result of that, the 117-page paper, is a proof of the promotion of Pixton's formula to the level of this Picard stack. And it says that there's a DR cycle, and it actually lives as an operational class on the Picard stack. And moreover, we know the formula for it in terms of the tautological ring. I'm not going to write that formula now, I don't think. Let me see. No, good. But that's not the direction I really wanted to say, because that's a direction that's kind of orthogonal to this talk, because it's about the geometry of this DR cycle of the Picard stack. If I'm interested in the Picard stack itself, say you don't care about the DR cycle, Pixton's formula always comes with Pixton's relations. If you go one lever further in the formula, you get zeros. And this was conjectured by Aaron, and it was first proven by Clater and Yanda, Emily, and Felix in the case of the Deline-Mumford case, and then Young-Han Bai proved it for target varieties. And in fact, in our paper, we show that actually those Pixton's relations give you actual honest, kind of really honest, interesting set of relations in the operational chow of the Picard stack. So you can really do geometry. There's some, and those relations are these kind of proto relations that you can pull back. If you pull back to MGN bar, you get Pixton's relations there. And our current view is that these might actually be all the relations in MGN bar. It's not so unlikely. So using these developments as motivation, there's a natural question: is there some kind of Pic CohFT which gives Pixton's relations, some analog of Pixton's relations for the Picard stack? So maybe it's some kind of hybrid construction with the 3-spin. I'm not sure. I mean, a work that's somehow a little bit related to this is that Young-Han and Hyunho Lo worked on some P1 kind of analogs of this. But this question is somehow about, like, is there some kind of 3-spin version? That would be pretty optimistic. But anyway, since I'm speculating on. And another direction is that, yeah, so what are kind of all the relations among these tautological classes? I said this study is very, very similar in spirit. Well, I don't know. It's kind of neighboring to this CohFT study. So you can ask for, are there any other essential relations in this Picard stack besides this comes from this Pixton's formula, or can we already generate all of them? These things are hard questions to study. But while we're speculating, why don't we study for all the other groups too? We look at relations in the tautological ring of the bun for all groups G. And before Andre says anything, I'll say connected. And there's some kind of nice thing you might think here. You take this bun, if you take this this stack of G bundles, there's the maximal torus. And I think roughly speaking, this tautological ring should be somehow the Weil invariant part properly understood of this torus one. And the torus one has Pixton's relations for every single torus factor or torus tensor product. So you get the Pixton relations go into the maximal torus many, many, many different ways. So you might think that somehow that the tautological relations for the G bundles on curves are somehow obtained by taking the Pixton relations for the maximal torus and taking some kind of Weil invariant aspect, some Weil invariant summation of that. So this is almost some kind of conjecture about one. So that's the question. Are there any other relations? Okay, where are we doing? Okay, that's it. That's enough speculation. I made it.
All right. Yeah.
So does anyone left? Did I?
No idea because everyone's here. I had some question from the beginning, which actually I think has been bugging me the whole time, but pertains to this, just maybe this, the cohomology of the Picard stack. So I was trying to figure out why something was absent from your original definitions of the Picard cohomological field theory, which is why aren't we taking sort of compactified Picard schemes? You know, instead of just looking at line bundles, you would think when the curves get singular, you'd want some sort of properness, especially if you're studying cohomology and whatnot. Why is that missing from the theory, or could it be there, or should it be there?
I mean, I think this is what the questions like this were why I didn't think about these things very much. In fact, in the kind of the first version, I mean, back when we were in graduate school, it was kind of a popular thing. Yeah, don't mention it. It was very popular to look at compactifications of all of this. And if you do that, you find there's all sorts of crap in that boundary, and you spend all your whole life studying those singularities, and then they don't give you any reward for it.
Well, I think for MG bar they do.
No, but
no,
here
because that's and these things have completeness properties. You know, I don't know, what's your view? But I mean, anyway, I think that what really changed the ship for me finally was understanding that Picard stack was just a perfect place for Pixton's formula, and this cured all my view about trying to introduce these bad things, these bad looking at the compactifications. We don't do that. We're thinking only of line bundles on curves.
And the fact that it's not proper as a map to the, you know, MGN doesn't bother you.
No.
Like it doesn't, and it doesn't cause problems for the cycle theory or the cohomology theory, because you're using cohomology of these.
Yeah, but you know, like this thing I'm
everywhere.
saying, MGN bar maps to my guy. It just maps to it. You know, because that is a family. It just maps there. So if we're doing something bigger than that. But anything if you want to restrict eventually to MGN bar, it's okay. But it's not the case that everything is for free. MGN bar, you know, I mean, yeah, it is the case that it might have been better if one could think about line bundles on curves and that whole stuff being compact. I grant you that's better. But yeah, one psychological step is just to walk away from that. Actually, you know, maybe this is a funny part to tell the story, but since it's late now here. Soon after I finished my PhD, I was sitting next to Drinfeld at MSRI, and we were discussing, there was some talk about stable bundles, and I asked him some question, and he said that, you know, he was educated in the former Soviet, I guess it was still, even then it was former Soviet Union, and a lot of ideas, it was difficult for some of these ideas to cross the boundary there. And he never learned stability, and he wasn't really interested in stability. He said that somehow that, you know, you shouldn't think about stability.
Just use the whole stack.
Use the whole stack, yeah. Exactly.
Yeah.
So I never looked at my PhD thesis after that.
No, but maybe to answer it in somehow another perspective on Jim's question, when we try to degenerate a threefold, we would still like it to be, you know, kind of nodal, right? We don't, so it means the fiber over, we really glue a smooth divisor, right? We don't try to.
You don't take one of those line bundles in the local curves and make it a torsion-free sheaf. I mean, what are you going to do with that?
Exactly, yeah.
Yeah, okay, yeah.
In this local theory of curves, you can also look at the local, I mean, you can just put the arbitrary rank 2 vector bundle on your curve, right? I mean, this would give you.
Yeah, you can do that. But, you know, there's I guess that this is related to some.
It's like the
jail 2. That's like the
jail
2, and I'm telling you, that's the violent variant part of it. I don't think you really get anything new there.
No, I worry about that because there are stable bundles, right, on higher genus curves, really stable bundles, and so that's, you know, maybe not exactly correct, but
yeah. Well, I kind of think that if you have, well, I mean, here's the reason why there's nothing there. If you take, if we're just taking one bundle at a time or all of them, one bundle at a time. If you have a bundle, even whatever whatever stable bundle you want on a curve, you can always deform it so it splits as a direct sum of line bundles, I think. Because you can.
Yeah, but in general, cohomology of whatever bundles on a hydrogen curve, it's an interesting object. I don't think it reduces to
That's
any kind of
true, but we're doing it.
well-invariant part.
No, it doesn't. It absolutely doesn't. But even the cohomology of MG
Yeah.
is a very interesting object. It's only in the stable range that I'm saying it reduces.
Oh, okay.
That's the thing. That's the claim. It's only in the stable range it reduces. Yeah, for that. That's right. The statement here that I'm claiming, of course, it might be false, but I'm still hoping for it. This one here, is this screen share still on?
Yeah, I see.
Yeah.
Yeah.
So this statement here is about this limit as g goes to infinity. It's saying that somehow there's all that complexity, but if I take the stabilization, all I see is that violent invariant part.
Okay.
Which I don't know, as I said, it might well be false. And maybe if I email Oscar, he'll tell me it's just wrong. In which case I'll delete this slide.
Yeah. Well, I'll go back and edit the video. And
Yeah, that's right. We'll have to blackmail Jim.
I'll make it password protected. This part of the video is password protected.
I think this has a chance of being true, but what do I know about this? I mean, anyway, the only piece of evidence for this is the C star case, because that is this literally is the statement that Oscar proves in that paper. That part I looked. In fact, if you remember at MSRI, I think we also looked at that paper.
Yeah, I think so. More questions?
I'm going to stop sharing. So I'll put the slides up on my webpage at some point.
Also, send me a link because
yeah, I'll send you a link.
I put all the previous slides and put the videos go on the seminar page. So well, we've been going for almost 2 hours.
Yeah.
So maybe one last call for questions, or else we.
Yeah, I have a question.
Sure.
Do you think it's possible to generalize it to orbifold curves instead of NGN bar?
Yeah, probably. I mean, I don't know. I haven't even thought about it. What about even for the? I mean, you want to look at but which way? You want like a CohFT for like Rth roots or what?
Yes, for instance.
I don't know. I haven't thought about it. I mean, that's a question you could ask just for MGN bar. I mean, just the Deligne-Mumford world, right?
Yes.
Yeah, I thought that with Dimitri a long time ago we discussed this thing, because if there were such a thing, then this was I now remember with Dimitri we once discussed this. If there were such a thing, then you could try to find a formula for the 3-spin theory upstairs, not downstairs. And we came to problems with that. Is Dimitri still here?
Yes, yes. Yeah, but I'm
Do you
not sure
remember
it's
this?
exactly, yeah, I remember this. Just I'm not sure it's exactly the same question.
It's not exactly, but it's not unrelated, because if there were, I don't know. It seems first that there should be no problem, and I think you can define things, but when we tried to use this perspective to solve for the Witten class upstairs, we ran into some problems, right?
Yeah. Yeah, I'm pretty sure it's not. There is no R matrix section on spaces of R spin structures. So capital R matrix and small R spin structures, but I'm pretty sure they're not compatible.
What's on your ceiling? What is that?
The solar system.
I see. Oh, look at that.
I was thinking it's a pizza, but
Dimitri, I think that solar system is not to scale. You should have the solar system's not to scale. You're giving your kids a misunderstanding of the universe.
Yeah, I already showed it to scale to Sophie, but Peter is fine with this so far.
But
I mean, there's also this discussion of defining these R actions on this MGNX beta, right? Or cohomological field theory.
Yeah, that's right. There's Young-Han started thinking a little bit about that. I don't know what the full statement about. There's some issues there that you want to change the betas, and this may be more confusing. I think the Picard stack stuff is simpler. but I think so probably something should work there too. I mean, and so, somehow that there's you need the notion of CohFT, and for it to be useful, there has to be the action and also the classification. You need these kind of three things, and it might be the case that this Picard world is of all of them the simplest one, and maybe actually prove a theorem, because there is this, as I said, there's this stability result by Oscar and Ebert. I don't know. We're gonna try.
Should we view this Picard stat as like MGN with X beta, where X is just BGN? I mean, in some sense, it's that, right?
Yeah, something like that. That's right. Yeah.
In some sense, it's the simplest case of that question.
Yeah.
Or difficult.
That's why we should do it. You should do the simplest case first. But anyway, that's the proposal, that in the spring we try to make progress on that conversation from 3 years ago. I hope you have some time in the spring, Andre.
Yeah, sounds like a planning meeting already started.
Yeah, exactly.
Yeah. All right, so it's now 2 hours exactly. So maybe I think we had a record attendance today in the seminar. So to those people who are not coming back next week, I wish happy holidays and happy New Year. And then we also thank Rahul for a very inspiring talk. And then but the seminar still continues, of course. I mean, there'll be one more talk in 2020. Well, thanks everybody, and we'll.
So how many people made it? I mean, did people?
What?
I mean, people really made it for the 2 hours? I know you were there. You had to stay there.
No,
If you graph,
right now.
you know.
It just like a minute ago there were still like 23 people, and
and it started with more.
Maybe 5 minutes ago, it wasn't around 30.
I see.
You were at 48. You were at 48 at one point.
All right.
Yeah.